What would happen if a killer asteroid were found on a direct collision course with Earth? How would governments respond? Are there official plans in place, and would they even let you know? Do we have the technology to knock one out of the sky or to destroy an asteroid? On this episode of the podcast, I speak with Andy Rivkin, Planetary Astronomer at John Hopkins University and a lead investigator on NASA's Double Asteroid Redirection Test, or DART, the world's first ever planetary defense mission. We discussed the plan to crash a satellite into the asteroid Dimorphos at 7 kilometers a second. The DART mission is of course just a test. Dimorphos isn't a threat to Earth, but this is a dress rehearsal that will teach us about impact dynamics in case we ever have to do the real thing. In this conversation, we cover the details of the mission and whether the satellite will plow straight through the asteroid or splatter. We also discuss the physics of making sure that asteroids don't impact Earth, and Andy will give a more realistic picture of how likely it is that we'll ever need this technology in our own lifetimes. I hope you enjoy. If you enjoy this content and want to help the channel grow, then the best thing you can do is like, share, and comment on the video, and of course subscribe if you want to see more.
Escaped Sapiens.
Let's say, just hypothetical situation, there was an asteroid 200 meters across screaming in towards us from interstellar space, or maybe it's got a long period so we didn't know about it. Is there an official program in place, or is there some strategy in place internationally to deal with that sort of a situation, or we're not at that point yet?
So there's lots to that. Interstellar space, the things like Oumuamua or Comet Borisov, right? They come in very, very fast. We're unlikely to have too much warning. So I think a lot of the scenarios that people think about tend to focus on things that give us somewhat more warning time. Mm-hmm. Having said that, the other part of the question there are absolutely international groups that are set up under the auspices of the United Nations. There's kind of separate but related groups that deal with sharing data and kind of making the calculations, and then a different group, again related, that sort of figures things out, like, okay, at what threshold do we actually do something? If you have a 5% chance that something so and so big is maybe gonna hit us on such a time frame, then we take this action. And if it goes from 5% to 20%, then it becomes another action. And so there are these groups in place, international groups in place to coordinate things.
But with, let's say, for example, Oumuamua was going to hit Earth. We had how many days warning did we have there?
Well, again, we didn't find out until it was past us. So these things are moving. The worst case scenario that people talk about, at least before we found any interstellar objects, was you can have, a retrograde comet, that was coming in at, I think it's something like 72 kilometers an hour, kilometers a second, 72 kilometers a second. And a lot of the things, not counting then the escape speed of the Earth, that would add a little bit more on the way in. So usually when we think about things, we think about things coming in at, a tenth that or less. If I guess to get at this another direction, this was not Oumuamua. This was something much, much smaller, and that really didn't have a problem. There was an object discovered in 2008 called 2008 TC3, and it was determined to be on an impact trajectory with Earth. And it was, kind of the size of the table that I'm sitting at that you can't see. It's 2 meters in size. So they didn't spot it very far in advance. They discovered it kind of 48 hours ahead of the impact. We knew that an impact with a 2-meter object was going to have zero effect on the Earth. It was going to, not make it through the atmosphere intact. But they, the telescopes that found it and the people that did the orbit calculations follow the protocol. The protocol is, they told the Minor Planet Center, et cetera. I don't think there was the Planetary Defense Coordination Office didn't exist at the time, but, the folks at the JPL and the Earth Object Office informed the proper authorities, and I guess the proper authorities, they determined that the JPL folks and the other folks who determined the orbit determined that it was going to hit the Earth near the border between Egypt and Sudan. And so the proper authorities told the governments of Egypt and Sudan, hey, there's going to be a fireball, an impact. No one's in danger. It's in the middle of nowhere. I don't think the population density is terribly high, if anything at all, out there. So that got exercised. There are, if you go look on the internet for 2008 TC3 and impact, there was a weather satellite that caught the impact, so you can see a little flash in the right place. And not long after that, a team was organized by Peter Jenniskens of NASA Ames to go to that spot and pick up the meteorites. So we have, that's one of the few things that, maybe the only one, that was spotted from being in space. Data was taken of it in space. The impact was predicted. They went and picked up the pieces. So the process worked. Obviously, in case of a real emergency, we would want much more than 48 hours warning. But in principle, if that was going to hit, instead of the Egypt-Sudan border, if it was going to hit Cairo, they would have said, by the way, this thing's going to happen. Don't freak out. We don't think it's going to be a big deal, but there might be a rain of gravel at about this time. So
I'm amazed that we have that sort of a precision that we can pinpoint to us. They're not enormous countries, that it's going to land here. That might actually have some interesting implications for who, politically speaking, who decides they want to spend money on the interception, for instance.
Yeah. The way you might think about it, I don't know if how much celestial mechanics you or your listeners might have. So there's uncertainty on the positions of all of these measurements, right? You spot an asteroid, you say, here's where it is, but there's some uncertainty associated with that. You fit the best orbit that goes through the points, but then the orbit has some uncertainty associated with it. If you have something with very little data, so the problem occurs, right? If you have an object where the uncertainty in the orbit overlaps the Earth's position at any time, right? Mm-hmm. That's when you might have a problem. There's plenty, and I don't know how many asteroids that have large uncertainties on their orbit, but because those uncertainties don't include the Earth in their positions, no one worries about it. As the positions get better, the orbit uncertainty gets smaller and smaller. And eventually, if you have something that is going to hit the Earth, you also know the time where that intersection is going to occur, and that means that you can project the asteroid orbit onto the surface of the Earth. So as the process goes along, in these exercises and these I won't say games, but basically these almost like a role-playing game that people plan out what they would do. It starts out where kind of an entire hemisphere might be at danger, but any given point on the hemisphere is not likely to get the hit. And then as the orbit gets better and better, that uncertainty region shrinks. In real life, almost every time we've done it, the uncertainty region would shrink, and then the Earth would no longer be included in it, and we're fine. In these exercises, and then in this one case where it hit near the border, the uncertainty region shrank to the point that you would say, okay, here's this line along the Earth that are the possible points depending on when exactly the asteroid shows up relative to the Earth's position. And then when you know that well enough, you could say, yep, it's going to hit in this region along the border.
The thing that I'm sort of surprised by is, even when we deorbit big objects in space, like Mir and these sort of things, there is a huge area over which the object might hit. And we know really well where that object is. Like, we've even had people inside some of these objects. And I guess what happens is that buffets around in the atmosphere, whereas for an asteroid, you just scream through the atmosphere. Is that the main distinction there?
Yeah, good shout out for Mir there for the Gen Xers in the audience. Yeah, that is exactly it. The atmosphere is 50 kilometers thick, 100 kilometers thick at the most. These things are moving 20 kilometers a second. So in the course of just the few seconds that the object is in the atmosphere, it doesn't get a lot of the specifics don't matter so much because it's only in the atmosphere for 5 seconds and it's going so fast. Whereas something like Mir or some of these other satellites, when they deorbit, they're kind of the amount of time that they're affected by the atmosphere, since the atmosphere is what's dragging them down, often can lead to these huge uncertainties on how fast they're moving at any given time. The density of the atmosphere at any given time where they are, and that changes over the course of the day, that can really have big effect.
So it sounds like, so we've only spotted one asteroid that came in before it actually hit. Is that the case?
I will hedge. There were one or two others, again very small. And for specifics that are kind of funny anecdotes, they were not able to make a prediction on either one. So one of them, they kind of, the automated software spotted it, and kind of the automated stuff was like, oh, this has a good chance of hitting the Earth in the next day or two. The problem is that the observations were made on the 29th or the 30th of December, and the impact was for January 2nd, so everyone was kind of off, no one was paying attention, and again, it was a really small object, so if it were larger and more of a problem, it would have been spotted with much more time than they had. So it was kind of the sort of thing that the first day people were back at work, they said, oh, huh. So that hit the Atlantic Ocean, they think. And then there was another one in 2016 where the data, it was another small one. It was kind of the specific places that would have done some of the follow-up were affected by clouds. That one hit, we think, somewhere in southern Africa. There are some security camera footage from a gas station, that caught the flash, and then these satellites and things. So those were all very small, the sorts of things that hit us a few times a year. So usually the problem with those is spotting them ahead of time because they're small.
But so it sounds like the most unrealistic aspect of the movie Deep Impact or Don't Look Up is that they actually saw the asteroid coming. It sounds like we're not even going to have a last ditch effort, especially if you detect something after it's already hit.
Well, I wouldn't say I wouldn't say that. These, objects that are the size of a couch or the size of a chair, we get hit all the time, right? Every time you go out and you see a shooting star, it's an impact. It's an impact by something maybe the size of a sand grain, typically. As things go up in size, they potentially get more and more of something to think about. The things that are, couch size, chair size, hit a few times a year. Something we get hit by something 4 meters in diameter about once a year. Again, that's going to be a bright flash. It's not going to make it to the ground intact. It might be unfortunate if your house is right under it. But we pick up the pieces for meteorites, and your house isn't going to blow up. It'll, maybe get a hole in the roof from some of the pieces. Once every few decades, we get hit by something maybe 20 to 25 meters in size. That's about the size that the Chelyabinsk, there was an impact over Chelyabinsk, Siberia, almost 10 years ago, of an object about 20 meters in size. That was not spotted ahead of time. It was coming from the direction of the sun. It hit during the daytime. There was an airburst over the city. It broke windows throughout the city. The main problem was that people saw this great big flash, went out to the window, kind of were looking out, and then the shock wave came a minute or two later, broke all the windows. So about 1,000 people were hurt. If we were to spot objects like that, though that's big enough that we could spot them. Again, the problem with this one is it was coming from the direction of the sun, so it was up during the daytime. We expect about 5 million objects of that size to be out there. We've found a tiny fraction, but again, when you kind of run the numbers, we think that they hit every few decades, somewhere on the Earth, maybe every 100 years, somewhere on the Earth. The Earth is big. Going from the other direction, the objects that the size that might kind of, and I haven't seen Don't Look Up. I vaguely know about it, so I'm trying to keep away from spoilers. But I have to get through the Spider-Man movie. I got to wait for that to get on. Watch Spider-Man first. I have to get through the Beatles stuff first. So eventually I'll get there. But something the size of a kilometer, we think, would be an impact that would be big enough to really cause serious problems for human civilization. But we think we've found all of them. We think we've found, we think there's about 900. We think we've found, if not all of them, practically all of them. We have reasons for thinking that, based on how often we re-find things. We can say, oh, here's another 1 kilometer one. Oh, we already found that one twice. We found that one 3 years ago, and we found it again 6 years ago. The number of new ones being found is really small. So we just don't think there are that many out.
So it's a statistical argument, more or less.
It is. And then also based on extrapolating from larger sizes, we think that given this many 10 kilometer ones, there should be about this many 5 kilometer ones. There should be about this many 1 kilometer ones. And then going from the other direction, we get hit by 1 meter ones all the time. So where do these things meet? And they both point to about, something you started by saying 200 meters. The object that the DART mission will impact, Dimorphos, is about 160 meters in size. So I know those numbers. We get hit by something that size about every 20 to 25,000 years. We think there are about 20,000 of them. And this starts to get into where it's a little more uncomfortable. We've found about 40%. So there's about half of them, maybe a little more, that we haven't found. And I don't know if you're a card player, if your listeners are card players, poker players. So once every 20,000 years, obviously that's not very often. We live, most of us live longer than a year, thank goodness. And once you start to think, okay, what are the odds of it happening during a human lifetime? The numbers still aren't huge, but basically it's like every decade there's a 1 in 2,000 chance that this happens. If you want to say that we know where half of them are and don't worry about half of them, that means a 1 in 4,000 chance. That's about the odds of getting dealt a 4 of a kind in poker. So every decade, the universe is dealing us a hand of no draw, 5 card, and odds are good. We're not going to get a 4 of a kind, but sometimes you get the 4 of a kind. So
well, let's say, for example, then so not sort of a last-ditch effort, but let's say, for example, somehow we spotted one of these, let's just say 200 meters across, and we had, say, 5 years, 4 years, like a decent amount of time. with the rockets we currently have, say Starship, something like that, could we realistically do something?
Yes, I mean certainly we would try. Um, the There are a few different approaches that the planetary defense community think are mature enough that we could realistically try, that we could realistically assess. One of them is a civil defense, So we didn't spot the Chelyabinsk impactor coming in, but if we did, we probably would have said, you know what, it's going to blow out windows. It's going to be cheaper for us to replace every window in that city and just tell everyone, this is going to happen. Prepare like it's for a hurricane or a tornado. If you want to go watch The Flash at exactly this time, you can do that, but then you've got 2 minutes to get away from your windows and get into the basement, because launching a mission to do something would not necessarily be cost effective. Now, whether the Russian space agency would say, look, we don't care, we're going to do something, that's up to them. That becomes a policy issue. But civil defense, is one approach. The kinetic impactor approach, which is DART, which I'm sure we'll talk about more, is another approach. The most powerful tool we have is a nuclear package, a nuclear device. The people that deal with this sort of thing say that it's not a nuclear weapon unless you're using it in war. So it's not a nuclear weapon, it's a nuclear device. Unlike in the movies, the idea would not be to blow the asteroid to smithereens. The conventional wisdom for all of these techniques is that you want to keep the object intact and just move it as one thing rather than have to keep track of 10 or 50 or 1,000 different things, some of which could still hit the Earth. If you can keep it intact and move it, that's thought to be the best option. So in this case, you'd have a standoff nuclear explosion, and then the between the shock wave and the heat vaporizing the side of the asteroid that's facing you, that you'd use as some kind of exhaust. You would try to move the asteroid out of the way.
And you try to do that presumably early enough that whatever impact you give it will be greater over when sort of integrated over its entire orbit before it hits you.
So the problem, right? You're worried about asteroid impacts, right? When the asteroid and the Earth want to be at the same place at the same time, right? So the Earth is moving through space at like 30 kilometers a second. It's orbiting the sun at like 30 kilometers a second. If you take the Earth's diameter and you divide it by 30 kilometers, you get a time. You get about 7. If you divide it by 30 kilometers a second, you get a time. It's 7 minutes. So it takes the Earth 7 minutes to move its own diameter in its orbit. So the idea is you want to either speed up or slow down the asteroid so that its arrival time is changed by at least 7 minutes. So this is much more. It's generally we tend to think of this not like a goalie in a net trying to, knock away a ball or a puck, but the way I tend to think of it anyways, it's two trains on tracks that cross. And one train, the Earth, doesn't have brakes. You can't change the speed of that one. The other train, you can throttle it up, you can hit the brakes. So the sooner you know that there's going to be a problem, the less you need to change the speed of that other train. If you spot it the day before and you look at the timetable and you go, oh, hey, this is going to be a problem, then you just can change the speed of that second train by just a small amount and you'll be fine. If you realize it 90 seconds before the crash, then you're going to have to take really, really drastic action to do it. So that's why this is, the planetary defense, we try to think of it as it's a whole strategy that's got lots of pieces. The mitigation technique you choose is going to depend on how much warning time you have, which points to the search aspect of it being really important. We need to support all of the pieces. We need to not just say, great, we've got a kinetic impactor that will work. Great, we've got we think these nukes will work in space, but also we need to have the telescopes to say, here we put this satellite up, so now we can look in the direction of the sun instead of having nothing able to look in that direction. And also the third piece, which is understanding the sizes and the compositions of these objects. If you find something that's metallic, it's going to be different. You're going to have a different approach than if it's rock. If something has a moon, it'll be a different approach than if it doesn't. Some of these things, like in these movies or these scenarios where you have very little warning, you're going to have to extrapolate from what we know about other objects. So we need to understand what's out there in general to be able to make the best decisions we can, or the best inferences we can.
In terms of, so you mentioned that you want to keep the object together, but let's say, for example, you couldn't deflect it, you just didn't have enough time, and so you go the movie route, and you somehow bore in. From a survivability perspective, is it better to have many small objects hitting the Earth, or as opposed to one large object?
I think so. This is edging toward the stuff that I know less about. The amount of, I don't know how the heat would couple to the atmosphere. I'm not an atmospheric person, and I don't do impacts. I could imagine that having 5 different, say, or 10 different impacts, all of which deliver the same total mass. Maybe the devastation in one specific place might be smaller, but I don't know if the overall amount of material added to the atmosphere might be as bad or worse. Plus, the way things go, right? Mass goes as the radius cubed. So if you broke it into 10, I'll make it easy. If you break it into 8 objects of equal mass, each of those 8 objects is only going to be half the size of the original. So you're not gaining that much. Having said that, I think if it came down, and this is utter speculation, if it came down to it, I think the hope would be, or the strategy would be, to try to make it so that as few objects hit the Earth as possible. So it probably would be to put as powerful a thing as you have up there, and you blow it into a zillion pieces, and at least some of those would not hit the Earth. I think that would be that would have to be the strategy, but that is that's speculation, and I'm not saying that is the actual strategy, or that people who thought about it more would advocate for that.
And if it was last ditch, you probably would just send up everything you had available and just hope, pray.
Well, it's funny. I mean, everything comes with a cost benefit analysis, right? If you're going to say that I don't know, 5% of your launches are going to fail just because you can't expect 100% of your launches to fail, then is it worth? There's going to be some tipping point at which your failed launches are going to cause more damage than they would have helped if they were successful.
For instance, if a launch goes off and it crashes with a nuclear payload, or that's also something.
For instance,
But okay,
I think the answer is, and I think this is the right answer. I think the answer is, make sure you do everything you can to not end up in a last ditch situation. And there are going to be some of these things that are more difficult to do that. But some of the things like your garden variety asteroids that are just in the neighborhood that are, maybe you say you don't worry about the smaller ones because they're not that, the atmosphere will mostly take care of them. But you say, here's the size at which we think they are worth, they would be worth doing something about if we knew they were going to hit. And then you do the best search you can to make sure you know where as many of those are as you can. I think that's the real answer.
But okay, so the real mission that we actually have happening is not nuclear armed, it's kinetic impact, right? This is the DART mission. Are you able to give sort of an overview, just a very brief sort of what is the DART mission and why is it awesome?
Absolutely. So the nuclear option, I guess I'll say it is literally the nuclear option for deflecting asteroids is not one that people want to have as kind of our only option, right? Right now, people think they could pull off the nuclear thing if needed, but that's really the only one that, and it's been tested on Earth. It is against all sorts of international law to test it in space. So by some arguments, it would also be illegal to actually use it. Although I think that would probably, if it was the only choice, I suspect people would, the Security Council would make it okay. So people have been looking for other options for a while. So the kinetic impactor technique is the idea that you take a spacecraft, you ram it into the object that you care about, and you use the momentum of your spacecraft, hitting it, to change the speed of the asteroid. And then, like I said, if you can change its arrival time by 7 minutes, then you'll miss the Earth. So, and then that also ties into the idea of a search. If you have enough time, that you can change its momentum by just a little bit. So the DART. So people have wanted to do a test of this technique. For a while. The Europeans did a study for a mission that they were calling Don Quixote in the late 90s, early 2000s. At least I think that's when it was. And in their conception, they had a observer spacecraft, which they called Sancho, and they had a impactor spacecraft, which they called Hidalgo. And so the observer spacecraft.
Who was the donkey and who was the donkey?
Oh,
this is his helper, right?
Oh yeah, Sancho was the helper, and Hidalgo is knight. It means knight in Spanish. So they didn't want to call, for whatever reason, they didn't want to call the impactor Don Quixote. So that required two spacecraft. The one spacecraft would be there, understand the system, measure the system before they changed it, and then the impactor would come in, and then the observer spacecraft would basically see what happened. But that required two spacecraft, and ESA, this was just not a high enough priority for them, so they opted not to follow up. So my colleague Andy Cheng, who's also at the Applied Physics Laboratory, the John Hopkins Applied Physics Laboratory with me, he realized that you could do it with one spacecraft if you visited a binary asteroid system and you impacted the moon of an asteroid. Something like 10 to 15% of asteroids that are about 1 kilometer in size have a moon. And so the idea is that, you have your, here's my props here.
For those who are listening, he's using cups to show us.
That's right. So from the point of view of the Earth, if the viewer is the Earth, and the mug here is the main body, and this little USB stick is the moon, it would move in front and then come around and move in back, and you could measure the brightness of what's going on from the Earth, you'd see it as a point of light. But as the moon moves in front, it would cast a shadow on the main body. It would dim a little bit. Then it would move out of the way. It would get bright again. Then when it moves behind, it would dim again. And you could measure. We can measure the orbit period of the moon that way. Lots of asteroid moons have been measured that way. And if you did that before and after the impact, you could see what you did. So the DA in DART is double asteroid. We're visiting a double asteroid system. We're going to hit Dimorphos, which is the moon of Didymos. And we're going to change its orbit around the main body by changing its speed. So we're going to change the speed of Dimorphos by something like 1 millimeter per second. The speed of Dimorphos around Didymos is something like 16 centimeters a second. So 1 millimeter per second is actually a decent fraction of that. The asteroids, when they go around the sun, near Earth asteroids, I said the Earth goes around at about 30 kilometers a second. Asteroids also go around the sun, near Earth asteroids anyway, at about the same kind of speed, about 30 kilometers a second. So I said we want to keep asteroids held together. We want to move them in one piece if we can. So that means that we don't want to give them too big of a shove at once. We think that we don't want to push them harder than their escape velocity, just as kind of a rough guide. Because we think if you push them harder than their escape velocity, then they'll just come apart. So, because we think they're basically gravel piles that are held together by their own gravitation. So you don't want to push them more than 1 millimeter or a centimeter per second. They're going around the sun at 30 kilometers a second. So that's a very hard measurement to make if you don't have a second spacecraft there, which is why the European Space Agency was like, we need 2 spacecraft. But doing it from the Earth, doing it in this binary system, we can make these measurements with telescopes from the ground. We don't need a second spacecraft. So DART is going to.
Does that mean you just have to observe them for a long period of time?
We have a few different approaches. The orbit period is a little bit short of 12 hours around Didymos. It's something like 11 hours and 55 minutes. We think we're going to change that to 11 hours and 45 minutes. Say maybe it'll be 48, maybe it'll be 36 or whatever, but something like that. So the trick would be, we've got the props again. We know, because we've been measuring this system for a while, we can say, okay, we know when it's going to move in front and back. We've measured this a long time. We can predict. It's just like a clock, When DART does the impact, if it changes the speed, it'll change the period. So let's say it changes it from 11:55 to 11:45. So, it'll come around and we'd say, okay, this is when we see it. Then we have the impact. And now it's going to happen a little bit sooner, right? It's going to happen 10 minutes sooner than it would have. And then the next time around, it's going to be 20 minutes sooner, because every time around, it picks up another 10 minutes. So
actually, you don't need to observe it for that long. It's just, you can just, after one orbit, you can determine.
In theory, if you had perfect data and it was clear skies and everywhere and all of that. There's also, along the same lines, we're going to have the Goldstone planetary radar should be looking at the system. Instead of doing that sort of dimming thing that I was talking about, the telescopes will do, the radar will be able to actually see the 2 objects in space as separate objects, and it will be able to say, okay, if before using the predictions from before the impact, we would have thought that they would be like this, but really they're like this. And so we can now make that actually direct measurement. Yes, in principle, we could know very quickly what the answer is. We are going to make these measurements for a few months to get as much data as we can, to make sure that things have kind of settled down. We also want to do this correctly. We want to not just offset from old data. We want to say, okay, now we're starting fresh from the impact. We're going to determine the orbit period as though this is a new object that we've never seen before, and then do the comparisons like that. Yes, hopefully we will know within a few weeks pretty much what we expect the answer to be, and then use the rest of the time to kind of do our due diligence. It's possible also, we're going to be generating debris in the system, and the debris has its own momentum that it's going to carry away. We have a CubeSat built by the Italian Space Agency we're going to release about I think it's 10 days before the impact. It's going to kind of back off a little bit, and it's going to pass by something like 3 minutes after DART does. So it's going to take images of the impact and take images of the debris cloud. So it's possible, depending on how long it takes that debris cloud to clear, that also would mean that we might not be able to make the measurements we want right away. It might be that the debris kind of obscures things a bit.
Why is it that, so we've been going to space for decades now. Why is it that we're only having sort of our first planetary defense mission occurring now? Is there some new technology that's come in that allows us to do this? Like, what's the difference, or is it just government interest? Or
it's sort of so planetary defense, when I really only started to be taken seriously, I mean, the long version, I'll try to keep it from being the too long version. Right when I was a kid, I was taught that we did not know how the dinosaurs died, right? That we just didn't know. And here were some theories. It wasn't until the early 80s that the idea that an impact killed the dinosaurs was really seriously proposed and started to be taken seriously. It wasn't until really the 90s that people started thinking about the natural, consequence of, like, oh, well, if an asteroid impact killed the dinosaurs, is anything else gonna, like, out there that we have to worry about? And so it wasn't until the 90s that these searches began. In the mid 90s, there was a comet, Shoemaker-Levy 9, that hit Jupiter. That I think was eye-opening for a lot of folks, that there are things out there that are still hitting planets today. This isn't the sort of thing that happened billions of years ago, and was a fluke for the dinosaurs. So it kind of took a while to prepare the scientific community in some ways. I guess that's the way to put it. I think having the Chelyabinsk impactor in 2013 in Siberia that I mentioned also was a real eye-opener. I think having there have been searches ongoing for the larger objects for a little while. Congress tasked NASA with finding the 1 kilometer objects early in the century, and so that started to reach its completion right at the time that this smaller one hit, and kind of helped give a push to find smaller ones. And so then, the question of, okay, well, what if we do find something? What are we going to do about it? Became more of something that we could think about for real.
I guess before the space program, it wasn't really in people's conception that we could do anything about these events, even if they had thought of the possibility. I'm surprised that it was only sort of later on that I didn't realize. When did we know for sure that an asteroid had killed the dinosaurs? When did that? When was that?
The first proposals and the finding of the iridium layer. So there was basically this this geological work that was done where people found in this particular stratum of rock in Mexico that there was an enhanced amount of the element iridium, and iridium is not real common in terrestrial minerals, at least not in the crust. And so this sort of realization that, where is iridium common? In meteorites. And that kind of came along with this Mexican oil company finding this structure that people kind of realized, wow, this is actually a huge crater. So this was late 80s, but since it was the Mexican oil company, they had had the data for a little while, but just weren't making it public because it's proprietary data. So that was really kind of early mid 80s that it started to be taken seriously, and geologists, science moves slowly when it comes to radical ideas, even if those radical ideas are correct. So I think it really took 10 or 15 years. It really was, kind of mid 90s. But I'm an astronomer, and I'm in the community. I study asteroids. So we were, it made sense to us right away. I suspect you might still find some geologists who are sort of more senior who maybe are still not quite sure.
But I suppose they must have dated that impact somehow to... Can they get a dating from the iridium itself?
They don't date the iridium, but they use kind of their usual terrestrial techniques to date the rock layers just above and just below. I think that's
just from erosion and that sort of thing.
Well, so rocks get laid down. This happened in a marine environment. So there was sediments that washed down, and got lithified, and then the big impact, iridium all over the world, and then the things that make, and then life went on in some cases anyway. Geology went on anyway, and made more rocks. And so kind of all over the world, they found, here's this layer that dates to 65, 66 million years ago. And all over the world, everywhere that we have rocks that are 65, 66 million years old, they have this extra iridium in them. So this crater in Mexico got dated to that age, and then there was rock layers in Colorado, in Italy, and all over the world that show this extra iridium.
So actually, you have an incredibly rich data set because you can use the entire Earth to date this. I'd never really thought about that. That's
and then the folks that study fossils, they already knew that rocks of a certain age had dinosaur fossils, and rocks younger than that didn't. And so, having the I'll say coincidence, not in the the co-dash incidence, not like it was luck, having the fact that this layer below which there's dinosaur fossils, above which there aren't, and that they're separated by a layer that has a whole bunch of iridium. It was just really compelling evidence, and that's why we now think dinosaurs were killed by an asteroid impact when we did not when I was a kid.
So back to DART then.
Yeah.
So this is a kinetic impact. So where this thing's going to come screaming in and hit the asteroid. We've already had missions that have landed on asteroids, right? So Rosetta and this sort of thing. Why is this technically more difficult than those sorts of, or why is it different than those sorts of missions?
Great question. So there's two pieces. One is that Dimorphos is the smallest object that we have ever tried to encounter in space. Didymos is about the size of Bennu or Ryugu, which are were the targets of the OSIRIS-REx and the Hayabusa 2 missions. But Dimorphos is about the size of one of the pyramids of Egypt. And DART is about the size of a vending machine. And then not counting the solar panels. If you count the solar panels, it's like a bus length tip to tip. So we are targeting something smaller than anything else we've tried to target by at least a factor of 2 to 3. In addition to that, Rosetta and Hayabusa and Hayabusa 2 and OSIRIS-REx all spent long periods kind of doing reconnaissance, kind of 10 kilometers away. What is this like? Can we land there? Let's pick out like 3 or 4 spots. And then came in at whatever, slow pace that they came in to touch. And even in Rosetta's case, or Philae's case, I guess, it was not just the nature of the surface was such that it still kind of bounced around. Hit hard enough to do that. So DART is coming in at 6.1 kilometers a second, which is quick. Enough. Yeah. It's enough to, go from New York to Washington. I always screw this up. In under a minute. So, and like I said, it's the smallest thing we've ever targeted. So you put those two things together and it's definitely a challenge. So it's not something that we have someone sitting with a joystick, or the console, hitting doing their special move to make sure you get there. There's this smart navigation algorithm, smart nav we call it, that is going to control the spacecraft in the last hour or so, and it's going to steer us in. Maybe it's the last couple of hours. I should know this. Sorry. It's like maybe the last 4 hours. I think it's the last 4 hours. Where we kind of give it the wheel and it steers us in. So that algorithm has been tested extensively. It's been tested with in situations that we don't expect to find. So given kind of extra, tested particularly robustly, and yeah, it's going to be very exciting. It's going to be part of the excitement is it's like I said, it's going to appear as a point, just a single point of light from the Earth. It's also going to appear as a single point of light to DART until those last few hours. And it's really most of the data we're going to get that we're going to use from DART itself is just going to come in those last maybe 10 minutes, last 5 minutes. That's where we're going to get these good images of the surfaces of these bodies that will help us interpret data.
What happens if you come screaming in and you miss? Do you just do another round of the sun, or like, is there another mission? Is there a plan B? What?
No, we come in and we hit. I mean, if we are confident, we feel really good. The engineers ran the numbers, and the numbers are as good as you could hope for. Like every NASA mission, there are contingencies for what you might do in case things don't go as you plan. But we fully expect that on September 26th, September 26th here in North America, September 27th. North and South America, I guess. It'll be September 27th UT, September 26th here in the Western Hemisphere. That we'll just have good news.
How does the so you're imaging? So the satellite itself is imaging the asteroid. Is that active? Like, are you shooting lasers out, or is it just passive? How does that work?
Yeah, it's passive. And actually, now I take it back. Now that I think about it, I think we hit it. Maybe it's like 23:15 UT. So it's maybe not quite December. Maybe it's not quite September 27th UT. Anyway, no, it's just images. There's one instrument on board DART, and that's it's a visible camera. which is very much like the LORRI camera on New Horizons that went to Pluto. It's derived from the same lineage. Basically, it's a offshoot, a variant. I don't know what's the right how to say it. I guess a descendant. Yeah, that's it. That's it. So it comes in and it determines, where for the first part of while for the first part of the time that it's active, or that we've given it the controls. Didymos and Dimorphos is behind Didymos. It's going to be seen as one object. So basically, it's told keep steer toward that object, and then at some point Dimorphos moves out from behind, and then it sees two objects, and then it's told, okay, now steer toward the second one. So that's it.
And that's completely autonomous. I guess it's like shooting down a missile or something. So we're pretty good at this technology at this point. Or is it? So you have this satellite. So DART is screaming in. What did you say? 6 kilometers a second, you said?
Yep.
So pretty fast. And then it impacts the moon of this asteroid. And so one thing I'm a bit curious about is, do we know how the momentum of the satellite will couple to the asteroid? Is this going to just plow through? Is it going to, is it going to leave a big do we have any idea?
So we think, so in a perfectly inelastic collision, right? It becomes a junior high school or high school physics problem. We know exactly what will happen. And it will change the period of Dimorphos by something like 7 or 8 minutes. But we do expect there to be debris. We expect there to be ejecta. That ejecta is carrying momentum. It's going to carry it in the direction opposite DART's incoming direction, more or less. So we think that's going to be the equivalent of giving an extra push. We don't know if that's going to be an extra 20% push. We don't know if it's going to be an extra factor of 2 or a factor of 4. There are laboratory experiments and logical reasons to expect any of those answers, which is part of why we're doing the experiment. In terms of could we plow all the way through, we expect there to be a crater. We aren't 100% sure of the size of the crater. I seem to remember 15 to 20 meters being what the impact experts were guessing. Again, that's based on their best estimates. There's other, the range of estimates is much larger. We do not, if it does not seem physically possible that we're going to disrupt Dimorphos. We are not coming in with enough momentum. There's not enough energy in the impact. It's too big. It has too much mass and too much self-gravitation for us to do that. We don't think we're going to plow all the way through. Kind of the way you might think about this is, like I said, it's about the size of a vending machine. And it has a mass of 500 or 600 kilograms, something like that.
So it's not super dense.
It's not super dense. Rock is something like 2,000 to 3,000 kilograms per cubic meter in density. And so the way you could think about it is it's coming in however fast, but it's when it encounters kind of its equivalent in weight, or its equivalent in mass, it's going to slow it down. Maybe it's a factor of 2 of that, or maybe it's a factor of 10, or who even knows. But still, it's not like this 500 kilogram thing is going to be able to go through 1 million kilograms of rock. So,
but it could be the case. Is it not possible that the asteroid is just very, very loosely held together? Because
Yeah.
didn't we have these cases with some of these? So I don't know if it was Rosetta or these one of these missions when it landed, it sort of its feet of the lander sort of went inside the asteroid. It was
Yeah.
loose, right?
Yeah, OSIRIS-REx went a few meters. I think it was maybe a few meters in, before kind of realizing it and leaving. Hayabusa 1, on the other hand, kind of smacked into the asteroid Itokawa and kind of flopped around for a little while before getting its act together and leaving. So we think that Didymos or Dimorphos is more likely to be like that second case in composition. But even on top of that, there's still this mass argument. Even if you have, imagine something crazy, 80% porosity, still, the Dimorphos is going to be 100 meters deep, and there's only so far you can go, and it'll be presumably in that kind of situation crushing the material ahead of it. So it's not like the way the physics works, and I'm not an impact person either, but my understanding of the way the physics works is the more coherent, if you have more coherent material, then you hit it and you blow it out. If you have more crushable material, then you crush it, but you don't really blow so much of it out. So it's still there to
it's like hitting a pillow or something. So in terms of so the ideal situation then is it easier to, so how does the physics work? If I wanted to move the asteroid, do I want it to be soft or do I want it to be solid?
I think the way we try to look at this is we try not to want anything because who knows what's going to show up. There are pluses and minuses to all of these, right? You can imagine that if you have a very porous asteroid, actually, I'll back up. We think that this extra push that I talked about from the debris, so that's related to a parameter we call beta that we talked about, this momentum transfer efficiency. And in the inelastic collision case I talked about, where you don't make any debris at all, beta equals 1. In these cases that we were talking about, where it's super porous and it just buries itself, beta is still equal to 1 because all of the momentum from the spacecraft still got transferred. It's still inelastic. It's just, instead of inelastic, like it just kind of sticks to the surface, it buries itself. All the momentum still transfers. You've still got a lower limit. It's still 1. If you throw off debris, we think that a solid hunk of rock would give you the most debris that carries the most momentum. So that's the kind of case where we think you might get a factor of 2, you might get a factor of 3 extra push. So on the one hand, that would help you move it more. On the other hand, that also means you have a more massive asteroid, for a given size. So whether you'd rather show up, and I think it would work out, again, speculating, that you would rather have less mass to worry about. That you would rather move less mass than more mass, which I think means you'd rather have the more porous body. But that might depend on, would you rather have a 50% porous body, so it's half the mass of the solid body, but if you're getting a beta of 3 for the solid body, then maybe that more than makes up for it. So it's part of the experiment.
I see. So it sounds like really you need to go and do this experiment a whole bunch of times to get an idea, because if you just have one impact, then okay, you can learn some stuff about that sort of asteroid, but it could be, there's there could be classes of asteroids that are different in composition.
Yeah, certainly you want as much data as you can get. Right now we have none. So getting one is the most important, right? That's the most important increment you can have. Also beyond that, we do have these models that the impact scientists use. They are all so they are predicting now what's going to happen, and those predictions are based on literally in some cases you have a cinder block in a laboratory and you shoot a BB at it, and you say, okay, we can now simulate that, and we can now do a really good job of reproducing what happens if you fire a BB at a cinder block. We can simulate what happens if you take a 2 megaton nuclear package and you explode it in the desert. We can do that. So if we take those computer models and we apply it to what happens if you smash a spacecraft into a 160 meter rock asteroid, here's what you get. So they will be able to test those simulations, and they'll be able to say, okay, now we think we've got that. Now we think we can match that. So we've matched this kind of rock getting hit by this kind of spacecraft in this gravity, with this porosity. And that reminds me that I should not derail myself, but I will note something else after this. So we know how metal differs from rock. So now instead of using rock in this equation or rock in this simulation, we're going to do metal. Now instead of something that's 160 meters across, we're going to do something that's 100 meters across or 330 meters across or something. So I'll also note that this is an international planetary defense is an international problem. Asteroids can hit anywhere and do hit anywhere, and that the European Space Agency will be following up DART by sending a mission called Hera to the Didymos system. They'll be arriving a couple of years after the DART impact, and they will be making measurements that DART cannot make. So we don't think we're going to be able to see the crater. Obviously, DART itself won't be able to see the crater it makes. We don't think LICHA will be passing by. We think LICHA will be passing by too soon to see that crater in its final form. We think it'll be blocked by the debris cloud. But Hera will be able to go back and go, okay, here's the crater, here's the size of the crater, here's kind of the area on Dimorphos that got affected. Here's a really good mass measurement, and so that then will allow us a next generation of these models to be tested. We can say, okay, here's what we think we have, and now we can again predict here's how big the crater is going to be, and then Hera can come by and test that. So ideally, yes, we do this test. If we had infinite resources and didn't have to prioritize what we did, then we do this all sorts of places. But even just the one test is going to be really important and really give us a lot of information.
One thing that I think about, just from my own research, is you have to apply for grants to get funding for these sorts of missions, I'm imagining. And so it could be that you find out all this wonderful information about, kinetic impacts of asteroids, and then we just unfortunately never get attacked by any asteroids. We never get, unfortunately, this knowledge is never useful in that particular application. Is there also an argument that this is useful for eventual mining of asteroids, moving asteroids into some parking orbit, or is that when people are putting forward their grant applications, does this make its way in there? Or
I think so I guess I know you use that as the setup for the question. Again, remember every decade we get dealt a hand of poker, and even if that hand doesn't get dealt for 1,000 years, hopefully this will will be useful to someone. Although I'm sure they would do follow-ups in that 1,000 years. There are definite applications. Some of the technologies being flown on DART, and some that have already been tested are already going to be useful. We are using rollout solar arrays. So when we launched, the solar arrays were rolled up like paper towels, and unfurled shortly after launch, and they're working. That's how DART is getting its power, and those will be used on science missions, other missions, where you need to save space, and now you can, instead of having to worry about folding things up and sticking them into you can stick them into smaller rockets than you might otherwise. Smart nav, guiding us in to this small target at 6.1 kilometers a second. You can imagine that if you want to deliver something with precision, say a penetrator, an instrumented penetrator, it needn't even be an asteroid. If you say, look, we really want to study this part of Mars or this part of the moon, or and you can know that you can come in really fast and deliver something to this specific spot. I mean, there's a landing ellipse, just like any other thing, but our landing ellipse is really pretty small compared to a lot of them, and again, you don't have to spend a long time doing reconnaissance. In terms of mining, I think I guess to back up a half a step, but related to mining, you can use the smart nav sort of thing, and it doesn't have to be 6.5 kilometers or 6.1 kilometers a second. You could use it when it's really slow too. There's no reason that you couldn't just say, okay, we've got this figured out, and instead of doing these rehearsals, or these specific things we're worried about, you can kind of hand it over to. It's another way to make spacecraft operations autonomous in a way that might be attractive for folks. Those are the obvious things. You can again imagine that if you want to put seismic probes down on an object, and then create your own earthquake, whether you use this sort of thing to say, okay, we're gonna put a whole bunch of penetrators down, and then the last one is just going to be the impactor.
So basically, there's the physics of the impact itself, which you learn about because this is something we've never done before, but also there's just a massive tech demonstration of the thrusters or the solar panels or whatever other tech you have on board. I'm a bit curious when it comes to this sort of a mission. Where does the main cost go? Is it the launch? Is it the design? Is it just operations? Is it fabrication? What's the main sink for a mission like this?
Our operations aren't very long. We are especially you look at and this is not intended as a negative. You've got say Spirit and Opportunity, right, which landed on Mars. They were 90-day missions, and then they ended up lasting for 14 years or something. We are launching in when we launched in November, and if the mission is not over in the end of September, at least the operations part, then we're in trouble. The scientists continue to make measurements for a few months later, but from launch to end of mission is 2 years, a little less. We are doing this during pandemic. So the some of the fabrication, some of the procedures that we would normally do had to be modified, especially early on when there was no vaccine, when there was no when we didn't know a lot about COVID, and so the social distancing and the rules were very very strict, and were like I said, we didn't know enough to know how to do it most efficiently, but they came up with all sorts of modifications that I think they'll now be able to use in the future, to say, well, we really don't need 20 people doing this. We don't need 20 people in the clean room. If we have one person or three people and someone holding up their iPhone, maybe it won't literally be their iPhone, on Zoom, but some sort of here's our VR equivalent. Here's our AR way of doing some of these reviews. The launch vehicle, we launched on a SpaceX Falcon 9. I think that was the first deep space mission that SpaceX has done. If you want to, you can argue about the car, I guess, but certainly the first the first deep space mission, that was doing something for, I'll just stop there. And whether hopefully right, the idea of getting these commercial companies involved is to bring the overall cost down. So what our launch vehicle cost was versus what future or other missions might have is going to differ. There was originally some proposals, some versions of this had us doing a ride share, and just kind of launching into Earth orbit and then kind of making our way out. There were various reasons that was not the plan that was decided upon, but you could also imagine that would take the launch costs down. So I think it's hard for me to pin exactly. This is the first mission that the Planetary Defense Coordination Office has taken from the start. It inherited one, or it took over one. So we DART cost less than a typical Discovery mission. Whether it's half or a third depends on what kind of time frame you're averaging or you're adding up. But I think the Planetary Science Decadal Survey, I don't know if that means anything to you. Every 10 years or so, the planetary science community comes together under the auspices of the National Academy of Science and the U.S. planetary science community anyway, and decides on priorities for the next decade. So the current such study is underway, and it includes planetary defense for the first time. So what they will end up prioritizing for planetary defense and what kind of mission budget they'll look for is TBD. I guess that's a long-winded answer, and I might not have even answered it.
Well, no, you sort of did. I mean, there is the breakup of whether you're spending money on, you've got a shorter mission, so you have less cost in terms of just personnel, for instance. So thinking of the future, what is the path forward to a comprehensive planetary defense plan? What are the components that you see as most important? What do you think the trajectory is in that sort of direction?
The consensus is pretty clear that having a search telescope in space is the next, is really what we should be doing. That should be what happens next. The Congress has, like I said earlier, Congress had tasked NASA with finding all of the objects 1 kilometer and larger. that's done. Congress has since tasked NASA with finding 90% of hazardous NEOs down to, or potentially hazardous, basically the ones we're worried about, down to 140 meters. So that search is underway. That involves both, right now it only involves ground-based telescopes. The Rubin telescope is coming online before too long, and that's going to be a major component of that. But a space-based telescope is seen as the other complementary component for kind of doing what Congress asked within a reasonable time. DART is obviously happening. There will be other other things that we can test. There are other techniques that people have proposed that maybe are not quite ready to be tested yet, but one could imagine before too long.
Do you have some examples along those lines?
Sure. So there's the gravity tractor, which is another one that people think is mature, and it is really a very elegant idea. Basically, it because all masses gravitationally attract one another. The idea is you send a massive spacecraft and you park it next to the asteroid you're worried about, and you let the gravity from your spacecraft kind of pull on the asteroid. And since you can control where your spacecraft is, you kind of, have to move it close enough that the R squared is such that the gravity from your spacecraft is non-negligible. So you have to keep it pretty close. When you do that, you can then kind of move your spacecraft and the asteroid should follow. Obviously, you need a very massive spacecraft, and it needs to operate very close to the asteroid, and it needs to do so for a pretty long time. We're talking about, potentially needing decades for this type of mitigation to work. But you don't need to touch the asteroid. It doesn't. The composition doesn't matter at all. You just need to keep this spacecraft operating close by. So there are, and it's a lot more controlled than either a nuclear detonation or a kinetic impactor. Where for a kinetic impactor, right, we're going to hit, and it's going to react how it reacts. It's going to move however it's going to change the orbit, however it changes it. And maybe you could have a string of 2 or 3 or 5 or 10 coming in one after another and move ever larger objects, but you're not necessarily going to be able to say, this is the orbit I want it in. Where, I want to have it hit the moon. I want to have it come around, hit the moon, take it off the board, just not ever worry about it again. While for the gravity tractor, in principle, you could say, here's exactly where I want it to go. So that's the obvious.
In the case, in the case where it's not super porous and it's just a solid object, you could also just tether your spacecraft, right? This is probably simpler.
So the issue with things like we're going to tie our spacecraft to the rock and we're going to just put a rocket engine on it, is that these things are spinning, right? And they're spinning with sometimes very rapid spins and orbit and rotation poles that could be pointed kind of wherever. So you're left either putting your rocket at one of the poles and saying, okay, at least we can consistently push it in one direction, or de-spinning it and then doing that, or just saying, okay, we're just gonna, when we're pointed this way, we're not gonna have the rocket on. When we're pointed this way, we are, and then in between, we're not gonna, we're only gonna have the rocket on for a small fraction of the time. In terms of a tether, that's actually one that people have been proposing lately, which is also really interesting. A lot of these, the things that I was talking about with the kinetic impactor and with these others, you want to change the speed so that the object is not right. So, like I said, so it doesn't come to the right to the wrong place at the wrong time, and that's because speed and position in an orbit are intimately connected, right? If you change the speed a little bit, then you will change the orbit, and technically speaking, and then that means that you're not going to come back to the place you're worried about. So a tether idea that people have come up with actually does something different. There's a proposal that you put a big tether on your asteroid, and maybe you'd have to despin it first, I guess. And if you make it a long enough tether, then you actually change where the center of mass is. And by changing the center of mass, now you change the orbit that way. So it's moving however fast around the sun, but now the center of mass isn't where it is in a different place. So the orbit has to change to make up for the fact that it's traveling, in a different speed. So you can imagine some of the tethers involved there are really long. We're talking about kilometer scale, 10 kilometer scale tethers to really make it worth doing. But
that's really clever. So you essentially just change the shape of the object and
change the center of mass.
So no rockets needed, nothing.
Yeah, I mean, constructing something like that would then be where the underpants gnomes come in. But that's it. So the part of the reason, I guess, backing way up in a sense, part of the reason that the kinetic impactor is the one that's getting tested is because it's straightforward. We get results quickly. We don't have to wait a long time to see what happened. And some of these others are both more technically challenging, and then you need to wait a while.
Is there an argument for having a kinetic impactor? Sort of, you launch a mission tomorrow and it sits out orbiting the planet or in the L2 point or somewhere, so that when we do see an asteroid and we only have a day's warning, it's already there, it's already ready, and you sort of just kick off? Is that something that people talk about?
People, it comes up. The conventional wisdom right now is that since an asteroid that you're worried about can come from any direction, and the orbit you want to, and what you want to do to it might differ, that if you putting something into orbit around the Earth and then having it go, it's not clear that you're better off doing that. Something like, right, what you're proposing, the Comet Interceptor mission, say, right, is going to sit around until there's a comet worth investigating, and then it's going to go to see it. But in that case, it just needs to get within a certain distance from whichever angle. It's not trying to change the orbit, right? So, so that seems to make sense in that.
So it doesn't have to have a big relative speed.
Yeah. You're not trying to do something specific with it.
I see. But maybe in the future, when you have your ideal system in place, you just have lots of craft in different orbits, and that's when you've got unlimited money, and this is something that you really worry about.
Yeah, well, I think the unlimited money case is you put your super high-powered laser, out at at the North Pole of the moon or something, and you just pick them off as they come in. But yeah, I think ideally, I mean, it's funny, and I know that that this isn't exactly what Don't Look Up dealt with in this case, but I know the metaphorical. I understand what Don't Look Up is doing metaphorically. There is a question, and there is a legit question. if we find something that's gonna impact in, the 2300s, do we do something about it, or no, I mean, there's another part of the issue, which is that we would never, given the nature of these orbits and our uncertainty, we would not know if it would hit in the 2300s. We'd know that there was a 50% chance of it hitting in the 2300s. But, if we knew something was going to happen, would we do something about it? Or would we say, wow, look, the 2300s, I mean, let the folks in the 2200s worry about it because their technology is going to be so much better. Would we have wanted people in the 1800s to have done something if they found something, or what? So there is that interesting question about how do we, what preparing for a future impact looks like, and I think that certainly what we're doing on DART and collecting data for people to use, and I think doing things on that level makes sense. It's not necessarily clear to me that, especially given how fast technology changes, that having a fleet of things at the ready that we'd have to either replenish every 20 years, or we'd say, yeah, here's this thing that, is using 2020's technology. Oh my God, what are we're risking our, we're depending on 2020's technology. Oh, this is terrible,
It's sort of in vogue at the moment to talk about making humanity a multi-planetary species, right? Is this then, talking on the unlimited budget once again, is this something that fits into the planetary defense strategy realistically, or is it not really it's not seriously discussed by people in your profession, let's say?
It's certainly not seen as planetary defense. I think that personally, not speaking for anyone I work for, anyone I've ever talked to, or anyone I've, the number of people who I think are going to be living off planet is going to be minuscule, I think, for the foreseeable future, certainly compared to the number of people on Earth. So the idea of, well, we've got, I don't even know what the most optimistic number of people most optimistic and realistic number of people want to throw out there is, if there's 50,000 people living off planet in 50 years, I don't see any way there's going to be 50,000 people living off the planet in 50 years. But if there were 50,000 people, that still leaves, 7 billion on Earth. And clearly, that's where we have to put our efforts, and that's where we have to put our resources, and that's where we have to put our, ethically, the idea that taking a small number of people and putting them on other planets means that now that's a solution to this issue of, the 7 billion people who don't go off planet. I don't think that makes sense.
But sort of playing devil's advocate a little bit, well, let me ask then, let's say, for example, a meteorite comes down and it's going to hit you. Andy Rivkin, it's going to hit you specifically. It's particularly targeted. Would you prefer to be hit by a meteorite and die, and then also have the rest of the people die, or would you prefer to, not exist in a universe that does have 50,000 people survive? If you know what I'm saying.
Oh well, sure. I don't think that. I think that if you look at it in an actuarial sense, seriously, right? I mean, what's the best way to save 50,000 people, or what's the best way to save humankind? And you could turn it around. Once you've got your 50,000 people on Mars, now do you need a planetary defense program from Mars? And do you not, what does that look like? Do you say, well, we're not going to bother putting as much money into it because, it's only 50,000 people. I mean, ethically, I mean, it's funny. I'm not saying, it seems like, but you would now presumably have to take that seriously at some level, right? Well, Mars gets hit by this many asteroids. Now we have to look out for this, and it's a fragile ecosystem. Maybe, look, we can't, if something hits within, it's easier to disrupt. I don't know. So I'm not.
There's less atmosphere to dampen the fall of the.
So you have to worry about smaller objects. It's closer to the asteroid belt. I think it's. I think whatever the future of humankind is, I think we should make sure that we go forward as ethically as we can, that we bring the best of humankind into space and not the worst. And I think the whole multi-planet species argument just doesn't resonate with me as a solution. So it's different to say, as you posed, sure, if I'd rather not have all of humanity die out in a single event. But I don't think that. But I think that makes it all the more important that we have to do what we can to make sure that all of humanity doesn't die. It doesn't mean that I'm going to try, or we should try less hard just because we've got 50,000 people living somewhere else.
Is this one of the reasons why you got into this initially? Like, was this sort of the pitch? It's meaningful to, people have different reasons why they do the research they do. Was looking at, being a custodian of humanity and I'm, these are big words and all this sort of thing, but was it in reality something that really drove you to enter the field?
Well, it's funny. When I started, and I told this story before, so I apologize if you've encountered it. When I was an undergrad, an undergraduate and in high school and stuff, and I had all sorts of friends who were, going to be doctors. And one of my close friends from college, went to med school and was doing bio research as an undergrad. And when we met, and, I remember thinking, boy, I don't want that responsibility, right? I don't want to be like, I'm going to ruin someone's day, we have to do this root canal, or we've got to, or something much more serious, right? I don't want to be like, have that kind of responsibility. So, astronomy, right? But yeah, as kind of working on asteroids, and the time and place that I was working on asteroids, when all of these searches were starting to be done and people were starting to take it more seriously, it did kind of appeal more that here's a thing that I am studying, that I have some expertise in, and seeing friends in graduate school and after, and again, absolutely no disrespect, people that are studying, how thick is the ice shell on Europa, because we want to know if we can, if there's any life under there, or we really need to understand the perchlorate fraction in Martian soils, because that will tell us about the habitability 2 billion years ago. And or we're studying the rings of Saturn because we want to understand how old the rings of Saturn are. All of these are important questions, and all of them, if you sit next to someone on an airplane and they ask you what you do, you might have to spend a while trying to get around to like, no, here's why this is important, and you wouldn't have realized it. You sit next to someone on an airplane and you say, yeah, I study asteroids, I'm involved with planetary defense. That's not something you need to spend a long time explaining. It is the sort of thing that is consistently showing up in surveys as one of the, one or two most important things that people think NASA should be doing. So, It is gratifying that maybe something we're doing will be something that people will look back and say, well, I'm glad they did this. I'm glad they started thinking about this in the 2020s. I'm glad they did this experiment in the 2020s. I'm glad they started thinking about it in the 1990s. So that is definitely it. Whether or not it got me into it in the first place, it is definitely a something that does keep us going.
It's sort of an interesting, as far as research goes, it's an interesting, some people that go into research just for the fundamental discoveries. They wanted to discover some new thing that no one's ever seen before. This has a slightly different flavor to it that's quite nice in a way, which I quite like. I'm looking at the time now and I realize we've only got about 10 minutes before you need to run away. And so I had two questions that I wanted to ask. One just popped into my mind because of something you said. So you mentioned that you don't think we're going to have 50,000 people on Mars, in the next 50 years. What are your thoughts in that same time period with respect to space tourism and mining? Where do you think we'll be in that sort of direction?
Yeah. So, some of you asked why I got into the planetary defense stuff, and I also have my research expertise. What I do when I'm not doing planetary defense is I study hydrated minerals on asteroids. So kind of asteroids, the minerals that have water or hydroxyl. So the sorts of things that the asteroid miners are interested in, at least one of them. So I've interacted with some of the space mining companies, and in part because it's I think this is potentially goes back to what I was saying. We should try to bring the best of humanity into space, and not the worst. And I think some of this space tourism, some of the space mining stuff has potential to go either way. And hopefully it will be something that is done for the benefit of people, that we can say we're doing this stuff and look at all this wealth that is enabling us to teach, to make vaccines available everywhere, to eradicate malaria, to we can the UN is getting some cut because, or whomever is getting some cut because asteroids are the common heritage of humankind. They're in space. The Outer Space Treaty says all of this stuff. That's ideally what would happen, right? At least in my view. We say Antarctica is, we've been working in Antarctica internationally for the benefit of humankind for decades, and we can take that to the moon and Mars and the asteroids. So the asteroid mining stuff I've been working with like I said, I have some expertise in some of this. I think there's great potential there. I think it's interesting, with the launch of JWST, with the idea that there can be these big telescopes that could be refueled, on a time scale of 20 or 30 years, that the idea that maybe that's where a market is. I know people have talked about a market for asteroid mining being refueling communication satellites. And so if you can create that sort of market, I guess, where you could say, okay, here's the next big telescope, the LUVOIR or something, the next big telescopes after JWST, the Roman space telescope. And if you could make them refuelable, then all of a sudden these companies might have a high profile refueling option to shoot for, to propose to. So maybe. I'm hoping that space tourism ends up not like Everest, where it's really specialized. You have to be super rich. It's very, very dangerous. It's very, very dangerous for a group of people that kind of do our guides as their jobs and don't necessarily get a lot of recognition and have great conditions, and that the only people that do it are rich or who receive the largesse of the rich. I'm hoping it is not that. I'm hoping it is more like, the way that air travel in the early days was some person with their personal airplane shows up at your state fair and takes people up for a 15-minute ride for $10. We'll see how it goes.
Yeah, I'd never thought of it in like however Everest is. I'd never worried about that particular image before. My worries were more to do with, is it going to be environmentally damaging and this sort of thing. That's where my sort of brain goes towards.
Sure.
In the interest of time, so we have the last 5 minutes. I have to ask you. So, just looking towards the future, if you could paint a picture of what your ideal Earth defense system would look like in the next 50, 100 years, and then compare it to what you think we're going to get.
So if you want to cover all of the bases, so I think we will get the survey of 140-meter asteroids done, whether it's as soon as Congress wanted or not. I mean, Congress didn't give enough money to make it happen on the timescale they wanted. So it'll happen sometime in the next 10, 20-ish years. At that point, the largest risk in a statistical sense comes from long period comets. And long period comets are very hard to find before they are making their, coming in past Saturn and Jupiter. We don't have a good sense of what is out in the Oort cloud, and the Oort cloud is super far away. And whenever we get together and at meetings and kind of kick it around, we've yet to really come up with a great plan for how to survey what's out there. Maybe it will be and part of the problem is that asteroid searches take advantage of moving objects. You image the same part of the sky over and over again, you see what moves, and then you predict where it's going to be the next night. You go there it is, you fit the orbit. Things out in the Oort cloud move really, really slowly. And so you're forced either into these tiny, tiny images where we can see the motion because you're covering such a small patch of sky, and you've blown it up so big you can see things move. But then you've got to cover the whole sky like that, or you wait a really, really, really long time, or both. And then being able to predict those coming into Earth again is a whole nother kettle of wax. So ideally, you'd figure out how to handle that problem. Realistically, what I think will happen is people are going to say, "Ooh, yeah, that's a really hard problem," and it's a low enough probability that we're just going to keep it in the stage of trying to figure out how to do it. And instead, we're going to look at the smaller objects, like the ones that impacted Siberia, go from 140 meters down to whatever size we think the atmosphere takes care of them. So that's an easier problem. We know how to solve that problem. It's the same problem we've been solving before, just with larger numbers of objects. So I think that is a likelier place we take the next surveys with these with the telescopes, and then maybe testing some of these mitigation techniques other than the nuclear one, and kind of demonstrate those. And
you're not a fan of the nuclear one.
I think that I think like a lot of folks, I think we'd rather not get in the habit of just kind of using them, So testing some of these other things, and some of these other things that have more promise for dual use with science as well as planetary defense. So I think that would be great.
There's 20 zillion rocks out there around us, but don't go thinking that same. There's 20 zillion rocks out there around us, but on some of those rocks you'll find our name. We've been pelted all throughout our timeline. The solar system's playing dirty pool. We've been pelted all throughout our timeline. Go ask the dinosaurs if that was cool. If we could evade, our day would be made. Something to strafe could keep us all safe, and doing a test would really be best to avoid those problems. So we're testing NEO deflection, and doing it for practice just seems smart. It's trying out orbital correction. The mission goes by the name of DART, that double asteroid redirection test. And just one flick should do the trick. Just one nudge and those things would budge. A little poke, not going for broke, would avoid those problems. DART will visit the Didymos system. A one-way trip, that won't be a fluke. So when hazards come, we can resist them without resorting to a giant nuke. And just one flick should do the trick. Just one nudge and those things would budge. A little poke, not going for broke, would avoid those problems. 'Cause it could get worse if we don't rehearse. We'll run aground and see what we found. First we detect, then we deflect. Practice planetary defense with DART.